Hello again and good day. I hope you enjoyed the first two lectures on high performance computing. You're well prepared, have your coffee with you and have a sheet of paper and some pencil and now ready to skip into the next session. Today I want to explain a few methods and algorithms for solving the matrices arising from the finite element method or similar from the finite difference methods, and we would like to solve a simple Poisson problem on a unit square. It's a simplified situation, but I guess it's difficult enough to explain the ideas behind the algorithms and to get an impression how the runtime behavior of the algorithms and methods will be. So let's skip into the problem I would like to solve, the Poisson equation. So here we have the model problem we would like to consider this session. It's the Poisson problem. We have in the two-dimensional problem. We're searching a function u depending on both space variables x and y, which satisfies the equation minus Laplace u. U is this triangle on the left hand side. This symbol is defined as the sum of the second partial derivatives for each space dimension, here with respect to x and y applied to the unknown function u, and this should be equal to the right hand side f, a volume function. And this should be satisfied for all x, y in the given region omega. And as you see, if we add some linear function to our function u, linear function or this operator applied to a linear function will vanish. So, of course, these functions cannot be unique, at least up to some linear function. To get some unique solution, we need some boundary conditions. In our situation, we assume homogeneous Dirichlet boundary condition. That means that the value of the unknown function is given on the boundary, and homogeneous means that it's equal to 0. So this equation describes the steady state temperature of uniform square plate with boundary held at temperature u equals 0. So you have some kind of metal. You can fix the temperature that with some ice cooling on the boundary, and you have some external heat applied to this metal plate, and you're interested in the temperature distribution. Other applications of this equation arise in fluid flow, let's say in porous media, or if you're interested in some electrostatics problem, probably you're looking for a field, but this field can be described by a potential, and this potential satisfies the Poisson equation. These are a few examples, but of course not all. Due to the simple situation that we have only a square, the simple operator is minus Laplace u, and also due to the simple right hand side, which is equals to 1, under this assumptions we have exact knowledge about the exact solution, where it's just a combination of sine and hyperbolic sine function sin h. Of course, when you would like to evaluate this expression, you will have some trouble with this infinity given here. You will, at first glance, would approximate by partial sums, so substituting the limit process with very, very large n. But up to now we have here no knowledge about the convergence behavior of this series, so we don't need how many terms we need to satisfy some specific accuracy. So let's try to find out what the convergent behavior is and how many terms you need to be sure that the approximation is exact up to 10 to the power minus 4, 10 to the power minus 8, 10 to the power minus 15. Of course, we have solved only the problem in the situation here for very simple domain, very simple right-hand side, and very simple boundary conditions. What will happen if we modify a little bit? Let's say f is equals to x, or f is 1 on one half of the domain and 0 on the other half, that you have some checkerboard behavior of this f. Do we know then already also the behavior of u? And even if we know the exact solution of u, how expensive will it be to evaluate this function of u? That's the reason why we apply numerical methods, and one of the one simple method is the find a difference method. In the find a difference method, we approximate our differential operator, and will this equation with our discrete differential operator then will be satisfied only on discrete points. How do we get an approximation of our differential operator? Therefore, we, assuming that the regularity is given as much as we want to have, we use the Taylor expansion of our function u to get an idea how to get the discrete Laplacian. So, Taylor expansion in the first variable, u of x plus h, will give this expression with some error term, capital O of h to the power 4. We do the same expansion with minus h, so every second term will have a negative sign, minus sign in front of the term, so that if we add the first and the second expansion, that we have twice u, this term, the first partial derivative will vanish. Then we have h squared half plus h squared half will give h squared of the second partial derivative. This third term will vanish, and then we have an error term to the power h to the power 4. So this 2 times the function u will bring to the left hand side. We divide by this h squared and multiply everything with a minus sign. Then we end up, due to the Taylor expansion of u, with a step size h by this expression. So this is an expression, it's an approximation of the negative of the second partial derivative with respect to x. And the error term is just as quadratic, h squared. If we have the same parameter h in the x and the y direction, we can approximate the Laplace operator by the discrete Laplacian, which is given here. And the error is quadratic, we'll make. So how do we go from the discrete Laplace operator to the find a difference method? Therefore, we introduce some grid or mesh, where we use here some mesh size, the equally spaced mesh between 2 green points. We have the mesh size h. H is 1 over n plus 1 when we use numbering from 0, I equals 0 up to n plus 1. So the interior nodes will have I from 1 up to n. So that we'll have n squared green nodes in the interior which are not on the boundary. On the boundary we already know the values of the unknown function, which is given by the Dirichlet boundary conditions. Here we assume the homogeneous Dirichlet boundary conditions. That means the u, all the green nodes on the boundary given here are 0. For all the interior nodes, we have to satisfy the discrete Poisson equation for each node. Here we have this 5-point stencil representation, usually divided by h squared. Here we multiply by h squared. So in each node, 4 times the node, the function value itself, minus the right neighbor, the left neighbor, the upper neighbor, the lower neighbor, should be h squared times the given function value. So we end up with n times n equations in all n squared unknowns. Now if we move everything, if we would like to update our in u at the indices ij, we move everything to the right, and this gives some kind of Jacobi iteration scheme. So we want to update our uij, everything we will know already, the information from the neighboring nodes, and the volume force are on the right hand side. This should be a plus sign, divided by the factor in front of the pivot element. Let's with 1/4, and we have here these index, the iteration index k+1, and for the old data k. Now this of course is some kind of fixed point scheme, which could be written as u k+1 equals m u k plus some right hand side. But this looks more than a vector or matrix vector operation. That means we have to map this grid function or this grid valued function with the indices ij to some vector from indices 1 up to n+1. So the natural ordering will be the lexicographic, where you always count from left to the right, from the lower to the upper row, which gives n plus n squared indices. If you use this ordering, the resulting matrix A, if you have some linear system in mind, A equals B or AU equals B, would look like this tri-diagonal system. This matrix itself, it's n squared times n squared, where each of these block matrices T and the identity matrix have the dimension n. Why does it have this structure? Just have in mind these 5-point stencil, then you have the center element or the pivot element, and then you have the left and the right element, which gives a -1 from to the left and to the right. And then what is the distance from the diagonal to the entries given in this identity matrix? This T is a n times n matrix. This is the n by n matrix. So the distance from this diagonal to the diagonal of the super diagonal blocks is also n. So this gives the -1 of the row above, which is the index difference is n, and also the -1 to the row which is below these central element, and the distance is also n. So you will end up with this structure. A nice way to write these specific matrix in the lexicographic ordering is by using the Kronecker product. Probably it's unknown to you, but it's nice. And even when we would like to compute the eigenvalues of our two-dimensional Poisson problem, it can be easily written by using the Kronecker product, as you will see later. So what's the Kronecker product? We have this matrix B and a matrix A. And this product is defined by just take the entry of your matrix A multiplied by the whole matrix of B. And then takes the next matrix multiplied by A12, the second entry of A, and so on. So the matrix B has Q columns and the matrix A has n columns. So here we have n repetitions in the first row. That means the first row has a sign n times Q, and we have m times P rows.
So we see that I, the identity matrix, Kronecker product T, always where we have an entry in our identity matrix replace the entry 1 by the matrix T. This was end up with this one. Or T, Kronecker product I, wherever you have an entry, multiply this entry or substitute this entry by the identity matrix I. So this gives this. And now if you add both matrices, if you have in mind that, have a look, the matrix itself, you have 4 on the diagonal, that you 4 in the diagonal and minus 1 in the off diagonals. So we should have on the diagonal a 4, but the 4 you will end up is just the matrix T, which is minus 1, 2, 1, and the 2 additional on the diagonal, this gives the 4. The plus, the minus 1 from the left and right neighbor is included in the matrix T. Minus 1 of the lower matrix is given by the row of identities, block identities, and the upper minus 1 is given by this block row. Okay. If we want to show this in a MATLAB example, it's easily done. So let's fix a parameter n. This is the sparse identity matrix, n times n. We how to build the sparse tridiagonal matrix. So we shift the diagonals by minus 1 or the super diagonal by plus 1. We will end up by an n by n matrix, and the entries for the diagonals. So we have 3 diagonals, each of length n. They're all the same, so a multiple of 1, and each row is minus 1, 2, or minus 1. And just shift it along the diagonals will give the matrix T. Using the Kronecker function of MATLAB and adding both Kronecker products will give our matrix n. The resulting structure we will see if we apply the operation SPI to the matrix A. The additional 4 vertical and the 4 horizontal lines are computed by the 4 additional lines given here, just computing where these values will be here between the 5th and the 6th entry, and also between here, here, and here. If you would like to compute or generally compute the discrete Laplacian in any dimension, let's say 3 or 4 dimension, it's just a generalization. What we have learned from the first dimension, which would be the matrix T. For the 2 dimension, it's T tensor product with I plus I tensor product T. You see T is on the first, and in the second position, the number of factors in our tensor product is depending on the dimension. And here you see T on the first, the second, and the third position, and so on. You can generalize this to any dimension you think of. At least you have enough space or memory on your computer. Okay, let's continue, and a few words on ordering. Obvious we have, or not obvious, but here we depicted the natural or lexicographic ordering, row-wise from below to above, and you will get the pattern of the matrix as shown before. We can use how to get the matrix using the Kronecker operation. There's also different orderings, let's say these coloring. All nodes belonging to our 5-point stencils have different colors, let's say. So we can, one example or one reason for this coloring is when you apply the Gauss-Seidel method, you can decouple all the red and the black nodes. So usually when you're doing the Gauss-Seidel method, you have update 1
one entry of your solution vector, then the next entry of the solution vector, then the next entry of the solution vector. You always have to wait, and the parallelization of this process is nearly impossible. By this coloring, you have a block of red nodes and the block of green nodes. And if you write down these resulting Gauss-Seidel matrix, you see that you decouple everything so that you have a 2x2 block system. And first you update all the red nodes, and then you can update all the black nodes. So you can decouple, and for each decoupled system, of course, you can apply some kind of parallelization. Other kind of ordering scheme, let's say, is this kind of zebra ordering, which is more like this is checkerboard or red-black. You have some zebras, which is other behavior, or you have some kind of diagonal ordering. Besides these orderings, we have three other orderings: the reverse Cuttle-McKee, the minimal degree or approximative minimal degree, or the recursive bisection methods, and they have better behavior with respect to the fill-in. Fill-in, which occurs during the Gauss elimination. If you have the k-step in Gauss elimination and you would like to eliminate entries below the pivot element. Let's say the k-step, so you want to eliminate below the case pivot element, the case diagonal element, which is of course non-zero, and we assume that that's the pivot element. And both elements, we have entry AIK, so it's in the adjacency matrix, AIK is non-zero, and also in the adjacency matrix AKJ is non-zero. So these entries in the matrix are not vanishing. That means the product is not vanishing. These effects, this is the rule for the elimination procedure in the Gauss elimination. So we have our Aij, let's say it's 0. And now we have to update due to the fact that this product is not vanishing. It means that you have some fill-in. This was probably 0, but now this is not 0 anymore. So this indicates AIK, that's in the adjacency matrix, it's not vanishing. You have some entry, non-zero, because this edge exists. This edge exists, okay. Due to the case elimination steps, you will end up, this is Aij, k plus 1, will also have some fill-in. So we can keep track if we update always the adjacency matrix in our elimination process, or in advance if we do some symbolic eliminations that we can predict where non-zero elements will occur. So what is the situation in the Cholesky procedure? In the Cholesky procedure is a little bit better in the sense we have the symmetry behavior. It's not of course, there's a strong relation between the Gauss elimination and the Cholesky elimination, but after the elimination, we have A equals L times L transposed. So the upper part is already known. There we can predict, we're able to predict the fill-ins. We have the theorem by Rose-Tajan and Lücker, which means let's assume that some kind of Cholesky factorization exists for our matrix L, matrix A, L times L transposed. Then we know that each element Lij is non-vanishing if and only if there is an edge path connecting the vertices I from I via the nodes P1, P2, Pk up to J from our adjacency graph, where all these nodes P1 up to Pk are smaller than the minimum of I and J.
Okay, we know already in advance, okay, we see our adjacency graph and can predict where entries in the Cholesky decomposition will exist. Okay, because let's go. Here we only know, okay, we are doing this elimination step, and due to the elimination step, there will be some fill-in. But at the end of the day, all the fill-ins, we know what would happen, can vanish. And again, this fill-in maybe, or at the end of the day, the entry Aij will be 0. But in the path, in the way to the final decomposition, there may be some fill-in. Okay, this knowledge, as by these given theorem by Rose, Tajan, and Lükern, we don't have for the Gauss elimination. Okay, that's the reason for the fill-in we have in mind, and now let's have a look at the reverse Cattel-McKee method. I want to reduce the bandwidth of this method, and this method already 60 years old is some kind of heuristics. So let's start with this model graph, and how does these Cattel-McKee algorithm works. First, we compute all the degrees of our vertices, so the number of edges belonging to one node or vertex, and then we start with the minimal, or the node with minimal degree. If we would start with this node, and this node will be the first pivot, the second and third pivot element, then there would be no connection between this and all these nodes which are not these three. This means in the resulting reordered matrix that we only have entries in the first column and the first, second, and third place. All the other, the fourth and up to nth entry in the first column are 0, because we take the connected one. And then we continue. So for this example, so we could start here, we could start there, but we start here, and that will be node number 1. Now we take the neighbors, all the nodes which are connected to this node. So which will be the second or third pivot element. Both have the same minimal degree, so they are same. Let's say we start here, and then this is number 3. So node number 1, node number 2, number 3. Now we next take the next level. The next level we consider all the nodes or vertices connected to the vertices of level 2. And this will be this nodes. And this nodes, okay, again we start with the, one criterion is, again, take the minimal degree, which will be, this is small, then we have 3, and then we have 5. So that's the ordering 4, 5, 6, 7. The remaining, the next would be, this is connected to the 7, this is connected to the 7, and this is connected to the 11. So all the remaining 3 vertices are connected to vertices of element level or level 3. And this is the largest degree, and here it's just random. We can choose 8, 9, and 10. And then the reverse Cattel-McKee is, instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we do it the other way around. Let's say 1, 2, 3, which gives this graph. So 1, 2, 3 from the last level, and so on. These, of course, may will have some not small bandwidth or envelope, but the fill-in is smaller than the Cattel-McKee method itself. Just have in mind this was intended to reduce the bandwidth or the envelope in connection with the Sky format. Okay. And what is the fill-in? As I mentioned, it was developed for the envelope or the bandwidth. But what is the fill-in due to the Cattel-McKee or the reverse Cattel-McKee? Just make some marks and make some crosses and try to find out. So the other method I would like to discuss here is the minimal degree algorithm. Again, the minimum degree algorithm is a heuristic for finding a permutation P, such that P transposed has fewer non-zero entries in its factorization than A. Not reducing the envelope, but in the factorization we would like to have less entries. And therefore we like to keep track of the fill-ins by the argument we have seen before. Okay, if the nodes are connected to, in the case elimination step, to the case pivot element, then these nodes also should be connected. And that we can consider this for the symmetric situation, or what we'll have in the non-symmetric situation. Let's see what happened here. So again, we start computing the degrees for each node, and we always take from the set under consideration a node with the smallest degree. That would be here. Again, as in the Cattle-McKee algorithm. So, but now we would like to keep track of the fill-ins. We know, okay, we have fill-in. We have this node, it's number 2. These both numbers, which will in the Cattle-McKee algorithm would be the next nodes, or nevertheless, these are connected to the node number 1, and the Gauss algorithm would predict some fill-in related to these nodes. When this would be I and this j, then we have some fill-in at the node aij. Therefore, we introduce this additional edge and delete these edges belonging to the node number 1, or let's say we don't consider them anymore in the following process. Therefore, we take the dotted lines. So the next step, let's say we take this node. For this node, the neighboring elements are already connected, so nothing will change. So the next step, let's say we take this node over here, and we see this node and this node are not connected. So if we will delete this or do the elimination, this would be the third pivot element. You will fill up, we have some fill in this matrix. So fill in and delete the edges belonging to this node and continue with this new graph. Always updating the degree of our vertices for the remaining graph. So next will be this node here, and we see 3 have a connection to 2, 4 has a connection to 2, but there's no direct connection between this node here and here. So if this would be node number I, that would be node number k, then we would have some fill in at the value I, ki, or AKA, depending which number is smaller or larger than the other. So, I'm sorry, it was not this. This was the next. So this is number 2, and we have some fill in here. So, and then now we have fill in here. This is small, this or this one, and this is 2 is the smallest one in this graph. So we continue here. The next one we have 4 times is the same situation, and it's up to you how to choose the next vertex and the remaining vertex. So that's the situation. So that was the black lines was the original connection of the nodes, and the red nodes are the predicted fill-in in our Koleski or in our Gauss elimination. The Gauss, if we have the Gauss elimination on this symmetric matrix. Okay. But if you're seen updating, introducing these additional edges, it's time consuming. You need additional memory in your computer. It's quite dynamic, not predictable, complicated. But the good thing is that you can rewrite the algorithm, ignoring these
or you have a different perspective, you can also do this algorithm, but on a different kind of graph, the quotient graph, and therefore you don't need the additional edges here, or you can compute them in some indirect way. But what is still time consuming is the update of the degree of each node. To get rid of this updating the degree of each node, there exist upper boundaries. So if you know upper boundaries, it's fine. Probably in some situation, if your boundaries are not tight, you will choose different orderings of the nodes. Probably one node should have degree 2, but your upper bound says it's 6, so there would be slightly different orderings, but at the end of the day, the approximative ordering scheme is quite as good. With respect to the film, even the minimal degree algorithm was some kind of heuristic. But on the other hand, computing the AMD, so the approximative, using the approximative minimal degree by using upper estimates is much faster. So there exist tight bounds that say that for the minimal degree and even for the multiple minimal degree, you have a runtime behavior of n squared times nm, where n is the number of vertices and m is the number of edges, where the approximative minimal degree algorithm has a runtime n times m, which is quite optimal. Okay, besides the Cuttle-McKee and the AMD algorithm, there exists also some nested dissection method. So you have the set of all your vertices and your edges, and just dissect these index this graph, so that you will end up on the left hand with a set D1 and with a set D2 and a separator, so that there's no direct connection from the set D1 to the set D2, always some in between. Of course, if you have in mind the 5-point stencil, there's no, if this would be the central node, that means, okay, you have the 1, 4, and 10, which are also in the blue set, or the green, but you have never from the red one. This gives some 3 times 3 block structuring, where always the block A12 and A21 is 0. If you have some Cholesky decomposition in mind, also the matrix L has this block 0. If you're doing this dissection recursively, the first step, you have this structure as mentioned before, and if you're doing this for the subblock 1 and for the subblock 2 again, you will end up with this kind of substructuring. Here we have done the dissection, we have a dissection. If you do a quadro section and you do the ordering or the numbering of the separator in a smarter way, you will have a better behavior with respect to the fill-in or even for the envelope. Okay. Applied to our model problem, what we will see is that we have only 5 non-zero diagonals for the lexicographical ordering or for the zebra ordering, or even for the red-black ordering, you have a fixed number of 0 diagonals. The diagonal has not this nice behavior, it's depending on n. So that means that the compressed diagonal storage is quite optimal in the sense that if you would like to use some solver only based on the matrix vector operation, that's optimal, because all these diagonal, if you take a minute and have a look, you see that they are almost non-zero. So there's no extra work we have to do. On On the other hand, the bandwidth, it's not optimal. There's depending on n, when the lexicographical or the diagonal ordering, which is n, and for all the other, like the red, black, or zebra, you have an n squared. So the bandwidth grows and far away from optimal. If you try to use solver where you need to store the envelope, you see that the lexicographical ordering needs n to the power 3. And the factor of n to the power 3 is 1, so 1 times n to the power 3, whereas the diagonal ordering is just 2 over 3 times n to the power 3. So both have the n to the power 3 behavior, but you will save 1/3 if you use the diagonal ordering. Now we'll come to the ordering schemes I mentioned before. And if you do the example on our unit square again, you will see that the fill-in, not the size of the envelopes, the fill-in. So do your Cholesky decomposition and count all the entries which are non-zero. You will see that for the number of unknowns which are close up to 10 to the power 7, you will have fill-in, which is around 10 to the power 8 when you're using the AMD or dissection method. So it's, of course, if you have 10 to the power 7 unknowns, you have 10 to the power 7 entries in your matrix. When you are then around 10 to the power 8 or 2 times 10 to the power 8, you have 20, in average 20 entries per row, which is reasonable. On the other hand, the behavior of the reverse Cuttle-McKee, which is almost the same like the lexicographical ordering, you only have a smaller constant in front of the estimate, but the behavior is worse and not as good as AMD or dissection methods. Okay, I guess that's now a good point to make a break. We will continue in the second part with eigenvalue estimates for the Poisson problem, let's say, for the discrete Laplacian. Okay, see you soon.